Buddha? So when you, yeah, so what do you think? What kind of numbers can you get when you find the zeros of a polynomial function? Real is correct. And integers are real, yeah. Right? Well, real numbers are complex, so real and non-real are real and complex imaginary. That's how we can distinguish. So real, you could say complex, and that covers the whole kit and caboodle. Because remember, complex is real numbers and non-real numbers. Okay? So real numbers and non-real numbers. And so here's a completely ugly polynomial in factored form. Okay? Woo, it's totally gross, right? I don't want to multiply that thing out. Please, Linda, please don't make me multiply that out. I'll be here until graduation. All right, so looking at that, I want to give you some terminology. It says, here's a polynomial in completely factored form where all the factors are linear. What do I mean by that all the factors are linear? What do I mean? When you look at all those individual factors there, why do I call the factors linear? What else is linear? What's a linear function look like? Can anybody give me an example of a linear function? F of x equals what? Straight line, folks. X. Right. Give me another one. F of x equals what? 3x plus something. Right? What's similar with the linear function and each one of these individual factors? It has an exponent, but what is it, Shane? No. Inside those parentheses. Oh, these things. Whoops, sorry, Haley. I was trying to get it to Kate, and I thought Kate was my athlete, okay. Sorry, I didn't mean to almost hit you in the head. All right. What's true about all of those? I didn't hit anybody. What's true about all those factors? First degree, right. A linear function is first degree, which means the highest exponent you see anywhere is 1. And if you look inside of all of these would have a 1 as they're written. And you say, wait a minute, that first one's squared. But if we wrote this out the long way, it would look like this. X plus 3 times x plus 3, right? So they all have the highest power you see is 1. That's our goal for today. No matter what polynomial you're given, you're going to be able to write it out in completely factored form, so all of your factors are linear factors, and they're going to look like x take away some 0. Okay, that's our goal for today. So let's see if we can classify each of the zeros here. First of all, let's name what the zeros are. So what's the 0 for this first factor? What's the value of x that makes that 0? -3. So if we were doing it out, we'd just pull it out and say, what makes that 0 when x is -3? So I put my first 0. My next factor looks like 2x minus 1. I set that equal to 0. And Austin, can you help me out with that one? What value of x will make that 0? Mm-hmm. Yeah, 1/2. Good, thank you. And what about x plus the square root of 2? What's going to make that 0? Solve for x. Negative square root of 2, right? You just subtract square root of 2 from both sides. And x minus the square root of 2 equals 0. What's going to make that a 0? Square root of 2, right? Okay. Whew, the next one. I don't know if anyone's going to be brave enough to take the next one on. Let's see. Let's see who gets the badge of courage here. Oh, gosh. I don't know how to do that one. Solve for x. We want that all by itself. So how do we get rid of that -4? Add 4 to both sides, so that's where we'll start like we always do. X plus 5i equals 4. And now how do we get rid of the plus 5i? Subtract. You undo it by subtracting, okay? So x equals 4 minus 5i. Okay, so I'm just putting that in parentheses so it helps me see it as a single number. So that's one of my zeros, 4 minus 5i. Oh. And so does anybody have a guess what the next one might look like? 4 minus 5i? What? 4 plus 5i, right. They're called conjugates. You can solve it the same way. Notice these two are called conjugates of each other. Conjugates. And the only way they differ is one has a plus and one has a minus. Otherwise, they look exactly the same. Okay? Now, anytime you have one complex imaginary zero, if I only told you one of these, the other one comes along for free. They always come in pairs. You would never just have one of them. Same is true with your irrational zeros. If you have one irrational number, you just change the sign and you have the other root or zero. Those always come in conjugate pairs as well. Okay, so both of these come in conjugate pairs. If you know one, you know the other by just changing the sign. You'll never just have one of those. Just think of your solving a quadratic. If you end up with something like square root of 5 underneath your radical, you're going to have some number out front minus b plus or minus that square root over 2a. So they always come together in pairs. So your irrational zeros and your complex imaginary zeros always are in pairs. All right. So if we were to classify these first 4 are in the big group called real numbers. And these 2, you could say, are non-real. All right. And then if you wanted to get really specific, you could say that the first 2 numbers right here are rational numbers. And then that these next 2 are irrational. So if you wanted to like keep breaking it down and breaking it down. And you could go further. You could say -3 is an integer. Okay, and that's where you could stop. And then over here, these, if you wanted to say one final word to explain them, they would be this one right here, complex imaginary. Okay, because remember, your complex numbers are real and non-real. Real numbers is a subset of your complex. So what's the degree of this polynomial? What's the degree? If you multiplied all those x's out, just you took each x and you multiplied them, what degree would you get? Well, if we square this, what's going to be the degree of x in this first factor squared? X squared, and then you'd multiply x squared times this, you'd get x to the what? Cube, and then x cubed times this x. 4, and then times that one. 5, 6, 7, right? And how do you do that as a shortcut? Remember, if it's in factored form, if your polynomial is in factored form, you just add up all of your exponents. And notice this would give you 7. So this is a 7th degree polynomial. How many linear factors do you see? Be careful. Because if something has been shortcutted by putting a square or a cube on it, you have to count how many factors that represents. So how many factors are really right here, x plus 3 squared? How many linear factors are there? 2, x plus 3 times x plus 3. So this has 2, 3, 4, 5, 6, 7 factors, same as the degree. Notice 7 and 7. Now, how many zeros does it have? Counting multiple zeros separately. What the heck does that mean? Means each zero, for each linear factor, you have a separate 0. So even though you have x plus 3 squared here, and you just write, can you get the door, Haley? So when you look at this, you just write down 1 -3 here when you're just listing the zeros. But you count -3 twice because there's really 2 factors here. It's x plus 3 times x plus 3. So whatever the multiplicity of your 0 is, you count it separately that many times or individually. So -3 would occur twice. A half only occurs once. Negative square root of 2 occurs once. So all these other ones only occur once. So you got 1, 2, 3, 4, 5, 6, 7. You've got 7 separate zeros. 6 of them are distinct. That's how we say it. 7 zeros, 6 are distinct. Okay, you got 6 distinct numbers up here, but you have 7 zeros. So you count the multiplicity. Is that all that we have for that one? Yeah. Okay, so let's take a look at this next one. Here's a function. Does that graph make sense with what you see up here? Does the graph make sense? The arms, how many twists and turns it has and all that? Based on a little review? Yes, no? Okay, why does it make sense, Shane? There's 2 turning points. With 2 turning points, the smallest degree we could have, 2 turning points, and the smallest it could be is 3, and that matches the degree of our polynomial. It's 3rd degree, right? The arm's going in the right direction? Yeah. The leading coefficient here is +1, which means your right hand is up and your left arm is down. Right arm up, left arm down. So far it makes sense. All right. So look, in algebra class up to now, if I told you to factor that thing, you'd say, sorry, I can't factor that. There's no way I can factor that. I don't know how to factor that. Number one, it's got 4 terms. I can't group them. There's no common factor. I don't have a greatest common friend here. So what do you mean, Linda, factor this? Well, we are going to learn how to factor this so that it's a bunch of linear factors. How many linear factors are we going to have, do you suppose? 3, because our degree is 3. So when we learn how to factor this today, we're going to learn how to factor this so that it's x take away some 0 times x take away another 0 times x take away another 0. Now, sometimes those zeros could be a positive number, and that means that this subtraction sign stays exactly the same. And when that 0 is a negative number, this will change to addition. Some of these numbers might be real. Some of them might be complex imaginary or non-real. Some might be beautiful little rational numbers. Some of them might be ugly. Oh, we shouldn't call it irrational ugly. All right. So let's see how we get started. Well, one of the ways you can get started to find a 0 of any function is to graph it. And if it crosses your x-axis at an integer, you're golden. So I've done the first step for you. What does this little picture tell you about one of the zeros of your function? What's one of the zeros going to be? 2, x equals 2. So this tells you that x equals 2 is a 0 of the function. So if it's a 0 of the function, what's my 2 for? What do I get? 2 for the price of 1. What else do I know if x equals 2 is a 0? What else do I know about the function? X minus 2 is a factor. Okay, and how you would get that is you would solve this for 0 by subtracting 2 from both sides, and there you go. That's what your factor looks like, and that's why it's called a 0 of the function, because your function is 0 at x equals 2. All right, so you've got your very first factor. Here you go. Okay, so this is my goal. It's not going to be my first step. This is my end goal, where I want to get to. So if I took this function and my first factor was x minus 2, if I only broke it into 2 factors instead of 3, what would this second factor right here look like? What degree would it have to have? If I pulled out one factor and it was going to be something times something else, what would be the degree of that factor in there? Second degree, right? Because I'd have to have a second degree, so when I multiplied x times x cubed, excuse me, x times x squared, it'd come back to x cubed. So the big thing in here must be a quadratic factor, right? Which is good because you know how to find the zeros or the solutions to something that's quadratic. So once you can find the solutions to the quadratic, you're going to be able to get these little boxes right here for your linear factors. So let's find that quadratic. How do we find it? We do long division. X minus 2 goes into, someone want to read me it? Because I have it off my screen now. X cubed plus what, plus what, plus what? Thank you. I'm glad Shane's willing to help me out. Okay, so we know we're going to move in one spot from our lesson the other day, line up our like places, like terms, so to speak. Okay, so x goes in there, x cubed, x squared time. And I'm not going to do this as if I'm lecturing. I'm just going to do this as if I did my homework. And so if you get lost anywhere along the way, just let me know and I'll be glad to help. I'm just going to sort of go ahead and do this. Okay, so there I am factored. So I now know this polynomial can be written as x minus 2 times x squared plus 3x plus 1. So you've done the intermediate step here. This is your intermediate step. Okay, let me write that out so you can see it. Intermediate. Your in-between step, our middle step, because our goal is to have all linear factors. And right now, our first factor is linear and our second factor is quadratic. So we go down here and we're going to write that right here. F of x is x minus 2 times x squared plus 3x plus 1. All right. Now remember our goal from part A. What is it? I forgot. We want to find the zeros of the polynomial, all of them. So let's set the function equal to 0 and solve it. Okay, so let's find all of our zeros. Because once I know my zeros, I know my factors. Boy, you're tired today, huh, Cameron? Okay. He's not bored. You yawn when you need extra oxygen to concentrate. That's true. It's a misnomer, one of those misnomers in life. So if you're tired, you need extra oxygen to do whatever you're doing. All right, so when you solve this first one, no big news. We already know that one of the zeros is 2 because we saw it on our original graph of our function. Okay, now how do we solve this thing? There are no factors of 1 that add up to 3, so I can't factor that as I normally would. So how do I factor this one? Or how do I solve for x here? Quadratic formula, right? Quadratic formula. Oh my God, I have to listen to Linda sing that song again. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. X equals negative 3 plus or minus the square root of 5 all over 2. All right. So there you are, your two irrational zeros. Notice how they come in a pair. Plus square root of 5 minus square root of 5. Negative 3 plus the square root of 5 over 2. Negative 3 minus the square root of 5. So you always get pairs of irrational zeros, just like you'll always get pairs of complex imaginary zeros. So there they are. They look identical. Everything looks identical except for one's a plus and one's a minus. Now I would just suggest to you that you put these in parentheses like that, just so you can try to see it as a simple number like 2 or 5 or negative 3. Okay. And now to fulfill your obligation, you go back and you write your polynomial in completely factored form. The 3 zeros are 2, comma, negative 3 plus the square root of 5 over 2, and negative 3 minus the square root of 5 over 2. Those are my 3 zeros. And now in completely factored form, the first thing I have to do is decide what my leading coefficient is, What is A going to be in my factored form? It's going to be the same A as in my polynomial form. So what's my leading coefficient up here? What's my leading coefficient? What's the 1? You don't see it, but it's there. It's 1x cubed is the leading coefficient. So that means I can just replace that. I can put a 1 there or not put anything there. So now I'm going to need a little more space on my paper because writing in those irrational numbers is going to take a little more space. I say x take away 2, done. X take away negative 3 plus the square root of 5 over 2, done. X take away negative 3 minus the square root of 5 over 2, done. Now that's done for me. I don't know for my math lab if they want you to distribute the negative sign. So let's do it, just so in case you have to do it for homework. You can let me know. I haven't done that homework yet. So that negative sign is going to distribute. So it's going to become x plus 3 minus the square root of 5 all over 2. And then I'm going to distribute this to the numerator here. And I'm going to get x plus 3 minus the square root of 5 all over 2. So notice how they look the same again, except for you have a plus and a minus here. Whoops, wait a minute, I screwed up. That's a plus square root of 5. Okay, plus. All right. Okay. And notice your subtraction changed to addition because your negative b term there was also a negative. It was negative 3. So I'm not sure what form my math lab's going to want, but if you can't leave it like this, just distribute that negative sign. And if you have 2 terms in your numerator, remember to change the sign of both terms. Okay? Any questions on this? This is now completely factored. All your factors are linear. Would you be able to check that? If I asked you to check to get back to your original polynomial, would you be able to do it? And how would you do it? What approach would you go through to check that? What kind of problem is that right there in front of you? What kind of problem would you be doing? What's the last operation? Or what's the operation? It's a multiplication problem. How many pieces are in the multiplication problem? 3. So when you have to multiply 3 things, how do you multiply any 3 things? How do you multiply any 3 things? You could go left to right. So you would multiply any 2 first, get your product, and multiply it by the third. So if you had to check this, you would probably start right there with FOIL, since that you know that when you multiply this out, you've got to come back to what? You've got to come back to this, x squared plus 3x plus 1. If you multiply that out, you've got to come back to that quadratic. And then when you multiply x squared plus 3x plus 1 times this, you'll come back to here. It would be really good algebraic practice for you. I can't ever force you to do anything, but it would probably be really good for your arithmetic and multiplication skills to use FOIL here and see if you can, on these two factors here, and then take the result and multiply it by x minus 2 to see if you can come back here. Okay, it's just a suggestion. So what's the degree of this polynomial? Here's the polynomial we started with. It was what degree? Third. How many linear factors do we have? How many linear factors? 3. 1, 2, 3. And how many distinct zeros do we have? Or how many zeros? 3. 2. Negative 3 plus the square root of 5 over 2. Negative 3 minus the square root of 5. Maybe there's a pattern going on here. We'll see. All right, let's try the next one. Oh, we've got a conclusion. This is really important. We've spent, 4 classes on polynomial functions now. So when we first started polynomial functions and graphing them, we said that a polynomial of degree n, now be careful with the language, a polynomial of degree n can have at most n real zeros. Now we're dealing with real and non-real zeros. So here's the conclusion. If a polynomial function is of degree n, and counting multiple roots separately, that's like the x plus 3 times the x plus 3, the equation has exactly n complex zeros. So now we can include real zeros and non-real zeros. So whatever the degree of your polynomial is, that's exactly how many roots you're going to have or how many zeros you're going to have. An nth degree polynomial can be expressed as the product of a non-zero constant. That non-zero constant is what we've been calling our leading coefficient. It's whatever our leading coefficient is. And then n linear factors. You'll always have exactly that many linear factors. Now, some of them might be shortcut and have a second or a third power on it because you group them together. And each linear factor is always going to have this form, x minus whatever your zero is. Okay, and that zero can be the number 2, or it could be 2i, it could be anything, real or non-real. And here's the last two things that you need to know, is what I've already stated, but here it is in words. If I tell you a plus bi is a zero of a function, a polynomial function, then its conjugate, a minus bi, is also a zero. Okay? These are conjugate pairs. That's what we call it. A plus bi and a minus bi are conjugate pairs. And similarly, if you have irrational zeros, those also occur in conjugate pairs. So if 1 plus the square root of 2 is a 0, you automatically know 1 minus the square root of 2 is a 0 of your function. Okay, so those always come in pairs. And if I don't state both of them, you know they both exist. You fill it in yourself. Okay? So let's take a look at one of those sort of give me an example of type of questions I asked you a lot of times to do. So here's a give me an example of. Find a third degree polynomial function, f of x, with real coefficients that has -3 and I as zeros. And when you plug x equals 1 into your function, out pops 8. Give your answer in both factored form and standard polynomial form, which means you're going to have to multiply it all out. So where do I begin? How do I start this thing? It's going to take us a while, so if we all pitch in, maybe we'll get there faster. So anybody want to start us off with taking some of that information and getting going here? I'm not expecting you to find the answer right now. Just, can anybody start us off? Excuse me? Yep, -3 is the 0. So we know x equals -3 is a 0. So that tells us if we solve this for 0, we add 3 to both sides. So that means x plus 3 is a factor, right? So I write x plus 3. X minus I. And how did you get that, Austin? I is a 0 as well. X minus I equals 0 is a factor, right? Whoa, we're moving through this. And Shane, what was your insight here?
We got the x plus I.
Oh, yes, of course. Even though I didn't say it, if I is a 0, what's the other 0 going to be? -I. So that's where you have to do a little thinking and fill it in. And -I is a 0 as well, because they always come in pairs. So Shane knows I don't have to do any work. If x minus I is a 0, is a factor, x plus I. Because when I solve that for 0, x is -I. So what's the leading coefficient here? I don't know. Okay. So I want to remind you about something you have done over and over before, so that you don't think this is like new work. When you are asked to find the equation of a line, usually you find the slope of a line, right? Sometimes it's given to you, sometimes you have 2 points. And usually, this is just a little side, usually let's say the slope was 3, you get this far. But you know you're not done because you have to find what B stands for, right? And how do you find B? You plug in a point that's on that line, right? So to find B here, you plug in a point, X and Y, that falls on the line. Well, a line is a polynomial, so if that works for a line, it should work for any polynomial. So here I am. I almost have this completely done, but I have to figure out what the heck A is. Do I know a point on this particular cubic? Yes, Austin says 1 and 8. And where did he get that from? Right? F of 1 is 8. So when X is 1, Y is 8. So now you plug in 1 everywhere you see an X. And for F of X, F of 1 is 8. So you put an 8 here, and you put a 1 inside the parentheses everywhere you see an X. Okay. Well, my first factor isn't too hard to do. 1 plus 3 is 4. But now I got to figure out what this is. And that's just a little review of multiplying out these two factors when it has an I in it. And if you, after we do it, you might remember the shortcut that we discovered a few weeks ago. So if we use FOIL, we do 1 times 1, we get 1. Look, our middle term and our outer term always is 0 when you add them together whenever you multiply conjugate pairs, because you get negative I and positive I. That always will be 0. Any two factors that look like that, like x plus 3 times x minus 3, you never get a middle term. And then you get minus I squared. And at the beginning of the hour, we said I squared was equal to negative 1. So that becomes 1 plus 1, which is 2. So when you multiply that all out, you get the number 2. And 8 equals 8a. So what's a going to be? 1. Oh, God, I had to do all that work to find out a was 1. It would have been nice if it was like 1/9 or something. So I felt like all that work was necessary. So that means you can go back and you can replace a with a 1. And lo and behold, you have completed your polynomial all in factored form. And Kahneman's like this, yeah, you should feel like that. It's amazing. You never really to be able to factor that polynomial. Oh, we're not done. We've done the factored form. Now we've got to do the polynomial form. Need a new piece of paper for me. So let's do that together. It's not hard. It's x plus 3. What was it? X plus 3, x minus I, and x plus I? All right. So remember, do your associative property, multiply your x minus I and your x plus I. That, remember, we don't get a middle term. We're going to get x squared minus I squared, which is x squared plus 1. Remember, it's the sum of perfect squares, which we never could factor before. So x squared plus 1. And then we multiply that by x plus 3. And we still use FOIL here. We get x times x is x cubed. X times 1 is 1x. 3 times x squared is 3x squared. And 3 times 1 is 3. So written out in polynomial form with descending order, looks just like this. Is that what we started out with? I hope. I don't have my sheet here. Is that what we started with, or did I make a mistake? Oh, I don't know what I started with because I didn't have the original polynomial. All right, so there it is. That's your original polynomial. So that's what you just factored. Again, you wouldn't have been able to factor that after Math 106 class or with any of the factoring techniques we reviewed at the beginning of the semester. Now you can factor that. It looks just like this. Real zeros and non-real zeros. So when you look at the graph of this cubic, how many x-intercepts are going to appear in the graph? How many x-intercepts are you going to see? Oh, controversy. 3, 1, 3, 1. Why'd you say 1, Buddha? Right. Two of your factors are imaginary. So those don't appear on your x-axis. They're not real numbers. So if you look at this particular polynomial, it should only cross in one spot at -3. So let's take a look at it real quick. Okay, let's clear out all these big, ugly equations. So what do we have? X cubed plus 3x squared plus x plus 3, zoom 6 to get my standard window. And there you see it. It only crosses once at -3. Okay, still has 2 turning points, but it has 3 zeros. 2 of them are non-real. 1 of them is real. Okay. All right, so it is, yep, go ahead, Shane.
Well, can you go back to the factored one?
Factored one right here? Yep.
No, like when we wrote it out as did you have used the X?
Back here?
Yeah, you used the X-intercept.
No, because the x-intercepts are used is going to give you -3 and 0, which you already know here. See, it gives you a 0. You mean, could I have used -3, 0 to come up with A?
Right.
Well, let's try it and see. So let's erase this, and let's try see what happens. Since you know -3 is a 0, is it going to help us find A? Well, we'll find out. Let's see. So I put a 0 here, I put an A here, and I put a -3 in here, right? Okay, well, let's see what that gives us. All right, so we get 0 equals 0 times A, and so does it really matter what those numbers are? It's not going to help. It's not going to help us because it's still going to be 0. Yeah, 0 is really helpful for finding the factors, but it's not helpful for finding that leading coefficient. But it was a good question. Okay, so that's why you have to use this information right up here. Okay. All right, now, folks, I want you to turn to the group activity from Wednesday's lecture, which is on page 4, I believe, right? You see how this, like page 4 and 5 is a group activity, right? And there's a group activity from today on starting on page 3 of today's lecture. So you have tons of problems to work. I would suggest that you do 1 or 2 from each one of these to make sure that you understand what's happening. In fact, a half an hour, you should be able to get through 4 problems, I hope. Work together. It will help. Use your flags if you need me. And we are now done with polynomial functions as of today. So if you can work through these fairly successfully, then you've really have assimilated and put together all the information that you're going to need to know for this part of the course, okay?